Welcome to the precipitation reactions video. Your narrator is Jim Hart, and I'm going to talk about what happens when we bring ions together that, when they are together, they make an insoluble solid. When that happens, we have what's called a precipitation reaction. So this is the simplest definition of what a precipitation reaction is. It's when you bring, where something that's newly formed falls out of solution once it's made. It's kind of different from when you are freezing something. You get a solid there too, but that's not the same thing. This is when you're creating something new and it makes a solid as it's formed. Here's an example. We'll start out with some words. Lead 2 nitrate. You mix that solution with sodium chloride, and what we end up with, there's the most condensed representation of lead 2 nitrate in solution, sodium chloride in solution. We want to know what happens if we mix them. Well, if we look at what happens, this is what actually happens. This is a picture of a solid forming when we mix these together. So we have two questions when we look at something like this. Is it possible to predict if a precipitate will form before we even mix the solutions? And the second thing is it possible to identify the solid without doing a complicated analysis once we do see the precipitate form? And the answer to both questions is yes. Yes, we can. And we can if we have access to our solubility rules. So if you haven't watched the solubility rules video yet, go back and watch that before you move on. Here's a list of solubility rules, typical list, the one I used in the solubility rules video. And I'll show you how to use this for our example of lead 2 nitrate mixing with sodium chloride. So when we mix these two things together, we saw that we formed a solid. But now we just want to say that we didn't even see that happen. We can predict whether or not a solid will form if we have our solubility rules handy. So when we want to think about what's actually in the container here, we have to remember what these symbolic representations mean. We got the lead 2 nitrate with an aqueous after it and a sodium chloride with an aqueous after it. It means that we've got lead 2 ions, nitrate ions, sodium ions, and chloride ions all mixed together now. So immediately after mixing, what we have in the container are lead 2 ions, nitrate ions, sodium ions, and chloride ions. And we're not going to worry at this point about how many of each there are. We're going to worry about that at the very end. Right now, all we want to do is identify what's there, and that's what we've done. And we can do that by the names. Lead 2. The first one listed is the lead 2 ion right here. Let me get the lead 2 ion right there. The nitrate ion, the sodium ion, and the chloride ion. Names of ionic compounds: cation name, anion name, cation name, anion name. That's all I've done to this point. So naming, very important once again. So that picture that we saw of these ions floating around surrounded by water molecules, they will come into contact with each other. So what we want to do is to look at the other combinations of cation and anion. We started out with lead with nitrate, and we started out with sodium with chloride. Let's switch the partners and see what happens. So bring up the Thinker Buddy, and let's go ahead and write formulas for these things. What ionic compound does lead 2 make with chloride? And what ionic compound does sodium make with nitrate? And in that sentence right there, those questions that are being asked, both those two questions, if you just take the name of the cation and follow it with the name of the anion, you have answered it. You can also then you can write the formula from that. So I'll go ahead and pause, let you go ahead and think through it, and I want you to write the formulas for what happens when you take that lead-2 ion and combine it with a chloride ion. What's the formula of the thing you get? What's the name too? And the same thing is true when you take the sodium ion and combine it with the nitrate ion. So I'll pause here and you restart when you're ready to move on. Formula for lead-2 chloride, formula for sodium nitrate. So all I did was took the sodium, first one is lead-2 nitrate. Took the lead-2, combined it with the anion from the second one, and then I took the sodium, combined it with the anion from the first one, and wrote formulas for it. That's the formula for lead-2 chloride and the formula for sodium nitrate. So at this stage, what we have are the reactants, then we mix them, and we get the products. I left the phase labels blank because we're going to need to consult our solubility rules in order to fill those in. If we look at the solubility rules, if I had remembered the ones with no exceptions, I could fill in the sodium nitrate right away, but in case I didn't, I'll just go ahead and go left to right. Lead-2 chloride. There's no rule for lead-2. I had to use the chloride rule. And I look, find chloride, look at the exceptions. There's lead-2. So that means it's insoluble, which means a solid forms, which means I write an S. And then sodium nitrate, I got two rules telling me that it's going to be soluble all the time. So that solid we saw form in that picture in the first slide of this, all this stuff, that tells us that that was the lead-2 chloride. We're not quite done yet. We still need to balance the equation. And that's what we're going to do. Notice I haven't approached even thinking about balancing at any stage. I wanted to identify the ions that are there, form the compounds, figure out if a solid formed, and then when I'm all done with all that stuff, now I'm going to balance the equation. So go ahead. I'll give you a chance to pause and then balance your equation. Remember the trick of using the formula for an ionic compound. If you have a polyatomic ion, balance the whole ion in a reaction like this. That means you don't have to go ahead and balance nitrogen and oxygen. Balance nitrate ions. That makes solving it easier, because on the left side here we got 2 nitrate ions, on the right we only got 1, so we can fix that by putting a 2 in front, and then we'd have to put a 2 in front of the sodium chloride to balance the sodium and the chloride. Remember that it's trial and error, and the more you practice this, the easier it gets. So let me summarize the process of predicting whether or not a precipitate will form when you mix two aqueous solutions together that contain ionic compounds dissolved in water. Step 1. Exchange the cation-anion partners and write the formulas of the products. Leave the phase labels of the products blank. Step 2. Consult the solubility rules. See if one is insoluble, and fill in the phase labels for both compounds. If a solid is formed, then you're going to balance the equation. But if only aqueous products are formed, that really means nothing happened beyond mixing. And mixing alone is not a chemical reaction. Mixing is just a physical process. And when we're trying to determine if a precipitation reaction occurred or not, precipitation reactions are chemical reactions. And if it didn't happen, you just mix these things together and you didn't make a new compound, all the ions are still floating in solution, we're going to erase the products and write no reaction. We're not going to balance the equation at all. Let me go over 2 more examples before I give you a chance to do a couple of these yourself. Let's start out with these 2 reactions. Copper 2 sulfate, mix that with sodium hydroxide first. Let's focus on this one. First step, let's write out the formulas of the reactants. Then we need to figure out what we're going to write on the product side. The best thing to do for me is I like to make that little box of the ions involved and then draw lines between the ones that were not paired together on the reactant side to get the different combination of cation and anion. So that means I need to take the copper 2 and connect it with the hydroxide ion, and I need, because copper 2 has a 2 plus charge and hydroxide has a 1 minus charge, I need twice as many hydroxide ions as I have copper 2 ions. I'm going to leave the phase label blank because I'm going to have to consult the solubility rules. I'm focusing on one step at a time here. I want to get the formulas right first and then move on. Sodium combined with sulfate gives me the other formula I'm going to need. And sodium is 1 plus, sulfate is 2 minus. I need twice as many sodium ions as I have sulfate ions. That's the right formula for that. Now I consult the solubility rules. I look and, well, the second product has sodium in it. I don't even need to think about looking at the solubility rules because I memorized the one that the ones that have no exceptions, sodium compounds are always going to be soluble. But I do need to consult it for the copper 2 hydroxide. I find hydroxide and I see that most hydroxide containing compounds are insoluble. Therefore, and I look, copper 2 is not listed as an exception, therefore I make a solid. That is an insoluble compound. I did make a solid, so that applies here. I'm going to balance the equation with trial and error. Put a 2 in front. I've got 2 hydroxides on the left, 2 hydroxides on the right, 2 sodiums on the left, 2 sodiums on the right, 1 of everything else. So it's balanced, and I'm done. Let's do the second example. Iron acetate solution mixed with magnesium nitrate solution. Start out by writing the formulas for the reactants. Exchange the partners to get the formulas for the products. Going to have the connection between the iron 3 nitrate. There's the name of the compound. And I need magnesium acetate. Next step is to consult the solubility rules. However, both nitrate and acetate are in the list of ions that have no exceptions, that are usually soluble, and no exceptions that are important to us. So both of these are aqueous. Now our rule 3 had the section that said that if only aqueous products are formed, nothing beyond mixing happened. That means that we're going to erase the products. Just erase everything over there and write no reaction. We're not going to balance it. We're done. Because all we did was mix these two things together. All we had were those ions in solution. Nothing fell out. We started out with what we started out with is what we ended with. So that's all there is to this. We'll let you go on, and on the next slide you're going to solve some for yourself with a Thinker Buddy. Use these 3 reactions in words and convert them to chemical equations. And if you have something that results in only aqueous products, then you didn't have a reaction, you're going to write no reaction. If you did make something a solid on the product side, you're going to write and balance the equation. Go through the steps, and when you're done, I'll give you a chance to pause here, and when you're done, restart, and I'll show you the solutions. This is what you should have come up with for those 3 reactions. Let us know if you have some trouble with these, but really, you just follow the steps. It's kind of hard to make a mistake. Last part of this video, I want to talk about net ionic equations for precipitation reactions. And it's really, what it is a way to highlight the important part of a reaction. For these simple precipitation reactions, getting the net ionic equation is very, very straightforward. It's really easy. So just do this. And this applies just to precipitation reactions. Now, later on, you're going to encounter other reactions and solutions, and their net ionic equations will be a little different, but we'll wait until we get to those before we talk about them. This applies to just precipitation reactions. So what we're going to do is write the formula solid formed on the right side of the equation. Then we're going to write the formulas of the ions free in solution that make up the solid on the left side. And then you're going to, when something is a free ion in solution, you need to show the charges on that ion. And if it's part of a compound that's written as a whole formula, you don't show charges. You're going to include phase labels for all this stuff. So let's go through an example to see how this is done. We're going to start out with one of the equations that we just balanced and predicted. The potassium phosphate and the magnesium chloride, making magnesium phosphate and potassium chloride still in solution. And so if we're going to follow these two steps, I'm going to write the formula for the solid product on the right side of the arrow. And I'm going to take each of these ions that are in there. I've got 3 magnesium ions and I've got 2 phosphate ions. And I'm done. That's it. And we read this as saying that a source of magnesium ions combines with a source of phosphate ions, and we can produce magnesium phosphate. Notice that we don't see potassium ions. We don't see chloride ions in this equation. Our net ionic equation doesn't include them because they don't do anything. They sit around in the container and watch the magnesium get together with the phosphate and make the solid. They just stay in solution. Nothing happens to them. I mean, we account for them in the whole equation by showing them together in aqueous form, but they're still floating around separately. Remember what the symbol, the AQ after a symbol of the whole formula means. That's what it means. They're floating around in the container. So that's it. You just follow those 2 steps and you've got a net ionic equation. Make sure that the double check you've got it balanced, got the right number of things on each side. Also check out the charges. Charge should be balanced on each side. And what that means is that the charge on add up to the charges on the product side. And if I look, the product side here is a whole formula, which means that the total charges add up to 0 on the product side. They need to add up to 0 on the reactant side too. I've got 3 magnesium ions. That means I've got a total of 6 positive charges. I've got 2 phosphate ions, which means I have a total of 6 negative ions, which gives us a total of 0 charges on the reactant side. So just a way to double check. If you've done everything right, you're going to be good, but if you make a mistake, then this is a way to catch it. Give you a chance to do a couple of net ionic equations from these balanced equations. So these already represent all the chemistry that's happened. You're just going to rewrite it to show the important part. So I will pause, or I'll give you a chance to pause, and when you are finished, you can restart and watch the rest of the video. These are what you should have. List the spectators after you're done. Just write the formula of the solid product, write the ions that go into it, all the phase labels are there, and just list the spectators separately, and you have answered the question. So this can be done for anything that involves ions in solution. Acid-base reactions, all sorts of things, oxidation, reduction. And the process for writing those types of equations is a little more complicated. It involves concepts we haven't talked about yet. So it's kind of silly to bring it up now. But keep in mind that later on you will probably need to look at some of those things. But at this stage, all you need to know is how to write a net ionic equation for a simple precipitation reaction. You can see there's just 2 simple steps to follow once you already have your balanced chemical equation. And that's it for the series of videos on reactions in solution. Thank you for your attention, and let us know on the discussion boards if you have any questions about any of this stuff.